Right, whenever you're ready.
So my name is Trimless. This is Alejandro, Tony, Jose, Ansar, and Daniel. And our project was the Trimless low-cost solution for accurate voltage current purposes, sponsored by Texas Instruments. And they posed us with the problem to reduce their drip current from 3 ppm degrees Celsius to ideally a 1 ppm degree Celsius. Implementing the part Ref 5025, and our a voltage reference is something that is a ground. So like if you're measuring something from the ground to this table, which is like 3 feet, you're referencing the ground as your reference. And these voltage references are the same thing, but in complex electrical components. And now I'll pass it off to Tony.
Okay. For the test procedure, we have an environmental chamber that sweeps from negative 40 degrees C to 130 degrees C, but for our test, we only ran from negative 5 to 125. We specifically designed a board to hold a socket, and we placed that unit on that socket into the environmental chamber. And we have a C2000 MCU that reads the temperature from the board, and it also outputs a trim voltage that applies directly onto the unit to kind of correct that temperature variation. So we have a 8.5 digital multimeter that reads directly from the output of the unit, and a Keithley to provide power for the system. So as we went along in the semester, we used 4 boards instead of 1 because each test kind of ran about 4 hours, so it makes more sense to put 4 units into 1 chamber and have that come out as 4 sets of data instead of 1. So we have a mux that switches between the 4 units. And to calculate ppm per degree C, we take the highest output voltage minus the lowest output voltage divided by the temp span, which is, in our case, 120 degrees C, and multiply that by 1,000,000 to get a ppm per degree C number. And then I'll pass it over to Jose, who's going to talk about the
All right. So if you pay attention to the lower left corner, you'll see the current temperature versus output graph of a high-grade model of the Ref 5025. The current ppm of this device is around 3 ppm per degree Celsius, and in the middle of the middle graph shows the same unit but untrimmed. As you can see, ppm increases as it hasn't been trimmed. In this case, it's around 62 ppm per degree Celsius. Now, the last graph shows the same untrimmed unit after our solution has applied a correction fit to the trim pin. And as you can see, we saw a 27 times improvement, equivalent to 2.3 ppm per degree Celsius. So in conclusion, we were able to verify that we can improve the trim of our Ref 5025 by applying a correction to the trim pin. In some cases, on average, we were able to reduce it to about 2.3, and our most efficient case saw an improvement to 1.9. Thank you.
All right. Any questions?
So your set here says that the board has a current performance of 3 ppm, but it looks like you measured 62 ppm.
So the part itself, TI has a trim process themselves. All right, so this is before the part has even been trimmed. It's around 62 ppm per degree C. It's obviously a CTAT. It's going down with temperature. And the way that they trim it is they adjust that PTAT source to sort of balance it out. So their current process that they have for this can bring them up to around 3 ppm per degree C on their high-grade part, their ID designation on it. So what we were doing is we were taking those untrimmed parts and trying to come up with an alternative trim process to see if we could get ideally that 1 ppm per degree C level. So traditionally the way you kind of did this was either using higher order fit corrections like playing off of the square nature of like temperature coefficients on resistors. And so you could use that to sort of amplify your PTAT a little bit and curve it a little more, sort of flatten it out some. Our method instead of that went off of understanding the temperature of the device itself. So this ref part has a temperature pin that gives an analog output proportional to its current temperature. So we use that as our input to our correction function, and use that to calculate whatever trim value needed to be added onto it. Yeah.
Do you know what the applications are for these voltage current references and why it's critical for them to be this accurate?
Yes, so traditionally most of these high performance references like this, or maybe like an even more like an LTC 1000A, these are used a lot of times in either analog to digital converters and such, where if your reference voltage on your A to D converter changes, then your output code on your A to D changes, and then you have some variance across temperature there. So by keeping this part stable, you get a more true reference as to what your current reading is in that system.
All right.
So
One last
just one-
question.
So you had a goal of 1 ppm, you got 2.3,
Mhm.
as good as 1.9. So you didn't hit your goal. What would
No.
you have done differently to hit your goal?
We think probably we would have had to come up with a different sort of topology. Some of the, so the way that temp pin that we were using to characterize our units went, it technically had around a 5% distribution on that. So probably if we needed to go about it a different way, we would use, instead of that temp pin, we'd have to develop something on our own that maybe would be analogous to it, but maybe more tightly controlled. So the hope was maybe you could come up with some sort of a system that maybe could be integrated into another later version of it. So it'd be much more analog defined instead of this. The reason why we went sort of digitally corrected into the DAC here is because it gave us a lot of flexibility to try different types of fit, different orders of fit. So we tried square fit, we tried cube fit, we tried piecewise linear defined fits. We tried all of these sorts of things to see sort of the behavior of them, sort of like how many points you had to characterize to get how good a result. And that was sort of the primary thing we were going for here.
Thank you.
All right, let's thank the team.